Hello, everyone. I'm from company Luxury, like it has been told. As you might know, our program runs on mobile devices, and so we have to do a lot about optimizing it for mobile devices so that it will run well. The problem, what are the problems with mobile devices? One of the problems is that we can't select what hardware we run on. We must run equally good both on $200 smartphones with a weak CPU and somewhat GPU, and we can just add some FPGA or anything else to make it run faster. So we must use what we can. So what is it? The first thing which we must obviously do is optimize the algorithm. I just have to mention it because before you do any further optimizations, you have to optimize your algorithm. For example, in our case, there was a problem that we multiplied the matrices in the wrong order, right? And as you might know, that the complexity of matrix multiplication depends on the order of which you multiply them. And we once optimized it, tried to optimize it using some advanced optimizations, and then we just noticed that we can change the order of multiplication, and we got that obviously almost for free. So don't skip that. This is an important part, especially for mobile platforms. But once you've done this, what options do you have left? Well, so obviously the most important option which you have is using SIMD operations. What does it mean, SIMD operations? They stand for single instruction, multiple data. I'm pretty sure that many of you have heard about that, but okay, what's the idea of that? The idea of that is just that in scalar operations, you take one register, take another register, and you perform a single operation of them and get a value which you put in third register, right? Or in one of these, doesn't matter. With SIMD operations, things can be much better because you take one big register, which in case of ARM and Neon, you have 128-bit wide registers. So you can fill it up with, for example, 4 floats, and you can execute one instruction on all these 4 floats. And it's much faster. It uses slightly more cycles per instruction, but on the other hand, it benefits because it operates on a lot more data. So the theoretical performance, for example, for floats, which you can get, is up to 4. Well, in my practice, it's typically around 2 or 3 or so. No, between 2 or 3. The profit in these operations is pretty obvious. You can use it for many image processing algorithms, and especially for various linear algebra problems. And that was many of the problems which we solve. So try using those. How to use them? To use them, there are different ways to use them. The first and the simplest of all the ways is just to use some computer vision or computer algebra or some DSP library. For example, yes, this is the easiest way. You can just use the library and everything will be done for you if it's vectorized. For example, eGen is a great header-only library for linear algebra. It's pretty well optimized, and it has a lot of different algorithms implemented in it. So if you have some linear algebra task, you'll probably need to use it. Also, there are some other frameworks, platform-dependent. There's NE10. It's a Neon-optimized library for some image processing and DSP on Android. It doesn't have many operations, but for example, it has hardware-accelerated fast Fourier transforms, so which isn't present, well, which is but isn't well supported in iGen. Accelerate framework, it's for iOS, and it has a lot of different image processing functions, and for DSP and linear algebra too. OpenCV, fortunately, is quite weakly optimized for Neon, but they have optimized it. They have optimized, like, from what I know, like 40 functions on the OpenCV 3.0. So if you're still using previous versions, this might be a good chance to move further. There are also available some commercial libraries. I've heard about them, but I haven't really tested them. There is some library which claims to be compatible with OpenCV and Neon optimized, but I haven't tried that. This approach has some pluses and minuses. Pluses is that you just use the library, right, and everything is optimized for you if it's optimized. On the other hand, if it's not optimized, then you have to move further and make some handcrafted optimizations. Yes, so which handcrafted optimizations can you make? There's an easy way to make them. For example, on GCC or Clang, it's vector extensions. You can just make this using or type def with attribute vector size and set your desired size in bytes, and then just use it as a common variables. After that, all common operations with these variables you've defined here will be vectorized. Like it has many operations which are supported for scalars. Actually, almost all operations supported for scalars. It can be loaded and stored into memory. It supports subscript operator for accessing individual elements, though it can be not as good because some architectures don't have a way to efficiently take a value from a neon register to a regular register. So it might involve storing it back to RAM and then reading back from RAM the value you need. It's subscript operator, which allows you to select. Well, there are some problems in it also, but there's a plus that it's cross-platform. You just write it once. For all architectures, it will be optimized both for SSE, AVX if it's available, and it will be optimized for Neon as well, and ARM64. So you just write it once. Also, in Visual Studio, this approach becomes available since they incorporated that you can now use C-Lang frontend for their backend. Okay, and it may produce. The problems with that is that not all themed operations are supported. There are some operations which are present in actual architecture but isn't supported in there. For example, Neon has an operation for to take one iteration of Newton method to take a square root of a value, and it obviously isn't available here. And it may produce suboptimal code, so you still need to profile, analyze, and maybe you'll come with a better solution. Other thing which you can do is by using themed intrinsics. Themed intrinsics, they provide custom data types and sets of C functions to vectorize your code. They're like, here's that function. You can just also use it and it will be vectorized for you. Generally, this is similar to the previous approach, but they may give you a bit better control and more operations supported. Once again, you have to, in this one, you have to write the different code for different platform. As in previous approach, you can just write one code. As in this approach, there are different intrinsics for Neon, different intrinsics for SSE, and so on. And you may also be able to write a better handwritten code. So about handwritten ASM code. Well, it's actually what you see as what you get in assembler. It's just what you write will be exactly in your program. So I've seen some benchmarks, and in previous years I've been able to achieve like up to 2 times better performance than the code using intrinsics. And I've seen such benchmarks that claim to do that. But right now, nowadays, I'd say that compilers are pretty good at optimizing your code. So if you just use vector extensions like in the previous ways, you'll get around 10 or 15% if you write a perfect code. The downside is that you also need to write a separate code for each architecture. You need to learn this. It's harder to create. And you may need some tricks to achieve the maximum performance, because in this way, compiler won't do any optimizations for you. It will be just to you how good you write. And there are some tricks which you might know in order to write the code optimally. Well, there's one simple trick that can be applied to everything. It's just to reduce your data types to as small as possible. For example, we had a bottleneck once in which we used doubles for profiling, then we obviously reduced it to floats, but then we were able to change that to integers and even to short integers. That was one of our bottleneck, and it obviously gave us from floats to shorts just 2 times performance boost almost for free. It may be not obvious sometimes how to do that, but you should do it if you can. Also, for Neon, you might try to use POD intrinsic. it hints CPU to preload some data from the memory into caches, and which will be used in the near future. It can be used as built-in prefetch intrinsic. If you use intrinsics, you should also analyze the assembler code to watch out for some moving registers around or extra load stores. Sometimes they happen, and you may be able to get rid of them if you write a handwritten code. So nowadays, compilers do a pretty decent job, and it's pretty rare. Like Eugene told, for FPGA, you should use loop unrolling, and because it makes more % of an actual job and reduces such unnecessary things like checking the loop bounds and so on. And also, one of the most important things is that you must use a proper memory alignment. Because if you have, for example, 128-bit wide registers, then to load or store the data to or from it, you must operate on memory locations which are multipliers of 16 bytes. Because otherwise on Neon it will most probably crash your device, or on Intel it will slow down your performance. So let's have some simple benchmark just to illustrate the tools that it's not scary. So it was one of our bottlenecks once. We just had to sum the rows of the matrix into some vector. How can we do this? Well, with the simple code we have there, on non-vectorized, you probably can't do it any better. Let's take a look at how well it performs and how the actual vectorization speeds that up. Okay, so we have a vectorized code in something like that. Vector type is just a type def, like I've showed it previously. Like that's using our type def. So you can just make a loop. It's almost similar and easy to make, and gets vectorized for you. So, for example, to compare the performance for different data types, you can see with simple code, it's obviously like 2.5 performance, 2.5 times faster than it was previously. So we got our boost. What else to do now? Okay, let's do some loop unrolling and try to check what's there. You can see that I did some loop unrolling here and interleaved the loads and actual arithmetic operations. And as you can see, it gave us approximately other like 10%, 10-15%, so it really helps. Okay, let's look at the profiler and the disassembly. So what we can see is that our vectorized code, it has some extra instructions, like I said, that they're sometimes here. But what's more, it's the 50% of this code, of the time that it takes to execute this code is wasted on the store, which is completely unnecessary in this situation. Well, it's necessary, but it's quite strange. It takes so much. It's that store which happens here. So what we can do with it, we can change the order in which we take the sum and just make that we pass the columns and save it to a value. Pass the next column, save it to another value. So here's the unvectorized code for that, and vectorized code was for that. And this is the moment where caches come into play. Because in this situation, if we just if we change the rows, then we won't use our caches efficiently, because cache line or on ARM CPU is 32 bytes long. It means that when you load the data from the memory, it doesn't load only the particular value you want, particular float. It loads the whole cache line with it into caches. So if you use only a single float out of these 8, then you just discard that all the data loading into caches, which happens. So this example on the left executes like 3 times longer than the example which uses a simple loop. And if we vectorize and loop and roll the code, then we will make load in this case 46 bytes long from the memory into caches, and we will use the cache efficiently. So if we take a look at the benchmark, it's the last one. It's another 2 times faster that we achieved with previous approaches. And for the last benchmark is a comparison of my methods on float with Agent. As you can see, Agent gave approximately the same result which I could achieve with my approaches, and assembler code was just like 5% faster than that. Well, for other problems, speed up is pretty much about the same. You can, if you have a problem and optimize it using neurons, then you can expect like 2.5 times better performance. Okay, what to use next if we've finished with that? We wanted to achieve even better performance, so we've taken a look at the GPU and on the GPGPU on mobile devices. Well, that turned out to be pretty tricky for several reasons. But what the reasons can be to use it? The reason is that the GPU on mobile devices is like 1.5 orders of magnitude, has 1.5 orders of magnitude bigger theoretical performance. Like, for example, on iPhone 5, the CPU has like 800 megaflops, GPU has around 30 gigaflops. On iPhone 5S, the difference is even bigger, it's like 50 times. The problem is that the GPU is very hard to utilize efficiently on mobile devices because it has some limitations. We managed to rewrite all our face tracking using the GPGPU, but it was pretty hard and took us several weeks to implement, but it was possible. The problem is that CUDA isn't available on mobile devices. OpenGL also isn't available on mobile devices, and on iOS it's only available if you have a jailbroken device, and on Android Google promotes render script for GPGPU. You have OpenGL libraries from different GPU vendors, but that's obviously not very cross-platform. On iOS, starting with iPhone 5S, you can use Metal for GPGPU, but we wanted to make things faster on slow devices, not on the fast devices, so that wouldn't be very helpful for us. So we wanted to try and utilize just OpenGL ES 2.0 to make some GPGPU and speed up our face tracking. So that's the pipeline which you can just use to process your data. You can just take an image, some data, put it into a shader. Then you have some result with processed data, which you can put in another shader with another data, and so on. And you can pipeline this. And the end results you can read back to the CPU if you want, or display on screen. But there are many common problems with that. First of the problems is that textures were designed to hold RGBA8 data. That's what GPUs were originally around for processing images. But on almost all phones starting 2012, you can use half-float and float textures for input in shaders. So effective binomial filtering for that is usually unsupported. On many devices, you can use as a target 16-bit half-float textures. And so you can render to them, and so you can have like 4 16 bits floats as an output, or 4 just 8-bit char components. If you don't have the half-float components, then you can emulate the fixed point arithmetic using the 4 chars which you have available, or you can emulate floating point arithmetic, but it's a bit tricky and requires more operations for encoding and decoding. The other problem is that OpenGL states change may be very expensive, especially the render target change is quite expensive, and in our practice to get around 30 or 40 per second or per frame that your device run at 30 FPS. And another problem is that the data read from the GPU to the CPU is very expensive because it requires to stall the pipeline completely. Yes, it stalls the pipeline completely, but there are some techniques for different platforms which you can utilize to make that read faster. Yes, general shell read pixels is quite slow for that task, but for iOS you can use the texture buffer cache And for Android, you can use graphic buffer. It's private API, but there's a way to use it. So tasks that can be solved in OpenGL ES. Well, months ago, I would be happy. I thought that I would be able to add that face tracking on the OpenGL ES, but at the end it turned out that our approach on the GPU worked like 2.5 times slower than it worked on the CPU. We tried optimizing that and playing with that for a little, but unfortunately that didn't help. But there are many tasks on the GPU on the OpenGL ES on mobile devices which can be used efficiently, and we use them. For example, for image processing, there are tasks such as image binarization, edge detection. You can use it also for half transform, so you may need to read the data back to the CPU a couple of times. So anyway, it will be faster than the OpenCVC implementation by a couple of times on average device. For half transform, for example, for line detection, it will take approximately like 15 milliseconds on an iPhone 5 on a 640 on 480 resolution. You may use it for histogram equalization. We actually use it in that way. Another good approach is to use it for some convolutions on the image, for Gaussian blur. We also use it that way for color space conversions. And there are many more available examples in the GPU image library for the iOS. For the other tasks, it depends on many factors, because the way the GPUs work on mobile devices limits them in many different ways. For example, on desktop devices, we were able to speed up matrix multiplication by really an orders of magnitude using OpenGL ES. So on mobile devices, if you try to make for example, to multiply matrices on it, it would take about the same time as on the CPU. So it depends on the tasks. Okay. Thanks for watching. Maybe you have any questions for us. Also, you may ask some questions about our face tracking if you want. Yes.
Do you have OpenGL?
What?
OpenGL.
No.
Yeah, we are in Ukraine. We can just ask for no, and it's enough. Who have questions? Yeah, I see. Okay.
As someone who's tried to write GPGPU code using just shaders, I'd like to ask, what's current state on OpenGL ES with branching? I remember that being a problem.
Yes, actually, branches are quite the problem on the GPU. It slows down performance a lot. Also, among other things, it's dependent texture lookups, which also slow down performance a lot, and that was one of the reasons that our performance wasn't good enough.
More questions? Okay.
My question is, which library do you use for iOS?
To optimize our code? Well, we tried to use agent, but for our particular problem, the problem was that we need to some parts of the matrix, not the rows in this way, but some parts of the matrix. That's why we had to craft our code manually to fix that, because I didn't find that in agent, which is otherwise a great library, but for this particular task, we used a handcrafted ISM code. What? Yes, Accelerate framework we use for some signal processing, but we use it for audio. We use it for fast Fourier transform, and it works great.
Who has more questions? Okay.
It is interesting from scientific point of view. It seems like you have optimized matrix multiplication.
Yes, we tried to do that.
Okay, so I think that A straightforward way has a numerical complexity O n in power of 3.
Yes.
And if I'm right,
Stress and yes.
the most
The fastest asymptotically way
complicated
is
has n in power
2.34, I think,
Oh, okay, so 30
or 30 something.
30 something. Okay. So what about your method? How fast is it comparing to that maximum known efficient method?
Well, we can just create some method out of the blue, you know, but that method which, but in general for matrix multiplication, the stress algorithm, which is 2.83 or so, is usually used for matrices of size about 100, and this algorithm has such a big hidden constant that, as far as I know, it isn't usable in practice. We tried to optimize the n square, the usual n cubase algorithm, because it's much easier to optimize from it's just easier to optimize, and our matrices weren't big enough to try the other more optimal ways.
Okay, I guess. Thank you very much.
Yeah, okay.
Yes, maybe not a questions, but replica to discuss. Before I remember era before CUDA appears, and a lot of articles about how to multiply matrix, how to calculate some graphic primitives using shaders. Did you read these articles, and did you see that problems of CUDA, first versions of CUDA, is almost like you are talking about? I think most of these problems are discussed already.
Yes, unfortunately I haven't read these articles, but yes, yes, it looks like that CUDA in first version just used the pipeline which was used for OpenGL, so that they share the common problems. Yes, that's logical.
Do you use the matrices for transformations or for some other calculations?
We use matrices for PCA, for example, principal component. It's used for shrinking the data in our case, to shrink the model.
Okay.
And
Any other questions?
We also use the metrics for, well, just our algorithm, which uses the regression. It's one of the one of the problems which need to be done in it is multiplying a matrix by vectors. So that's for what? No, not for world transformations.
Other questions? Yeah.
I wonder whether the precision of half floats was always enough for your computations.
Well, the precision of half float was it's approximately like a bit more than 3 decimal digits. It's like 10 bits. And for our computations, it was enough. It wasn't a scientific problem. It's just a problem that it would look good enough on the user, and it did. It did. So it was enough for our case.
Okay, Fedor, thank you very much for this presentation.